Imagine opening your favorite app, TikTok, YouTube Shorts, Instagram Reels, and the very first video hits exactly the right vibe. The next one? Even better. It feels like the app somehow knows you on a level that's almost unsettling. But here's the twist. Behind that experience lies a war. A war between chaos and order, between billions of unpredictable user interactions happening every second and a machine learning model desperately trying to keep up, to adapt, to predict what you'll love next. And until recently, the machine was losing. But then came Monolith. Today, we're diving into one of the most fascinating engineering feats in real-time AI. A system designed at ByteDance, the company behind TikTok, that dared to rethink how massive-scale recommendation models learn. Not eventually, not overnight, but literally as you swipe. Before we dive into this world of collisionless embeddings, streaming engines, and real-time learning, hit that like button, subscribe, and turn on notifications. Because the more people who see this breakdown, the more we'll be able to bring you deep, cinematic explorations of the algorithms shaping our world. All right, let's step inside the machine. The digital universe of recommendations is nothing like the calm, structured datasets of classic deep learning. Forget well-behaved collections of images or neatly labeled language corpora. Recommendation data is wild, chaotic, and constantly shifting. Every user brings their own universe of behaviors. Every video or item is a fleeting star in a constantly changing sky. And the features behind these interactions? Almost entirely sparse, categorical, and extremely dynamic. This leads to two massive problems. First, the curse of sparsity. Every user, every item, every context becomes an ID. And IDs aren't limited like words in a dictionary. They explode into the billions. It's as if you tried to build a library where every page of every book needed its own custom shelf. Embedding tables, the maps from IDs to learned vectors, balloon to unbelievable sizes, too big for a single machine to contain. And even worse, they grow every day. Second, the enemy known as concept drift. Humans change constantly. Today you might binge comedy clips. Tomorrow it's cooking tutorials. Next week you're suddenly obsessed with Korean woodworking videos at 2 a.m. No judgment. But to a model trained on last month's data, you're unrecognizable. Most frameworks were never built for this reality. TensorFlow and PyTorch separate training from serving. First, you train models offline. Then you deploy them. But that break, that delay, is deadly. Because by the time your model sees what was happening today, it's already yesterday. Monolith was born out of necessity. ByteDance realized that no existing system could handle the fire hose of real-time behavior powering platforms like TikTok. They needed a model that could learn continuously, adapt instantly, and handle a universe of sparse features without collapsing under its own weight. The first breakthrough is something deceptively simple, a collisionless embedding table. It sounds innocent, but embedding collisions are one of the silent killers of model quality. Most systems use hashing tricks to force IDs into a fixed-size table. It's like assigning thousands of people to a small apartment building and telling them to share rooms based on a magic number. If two random strangers get the same number, congratulations, now they share a bed because the system thinks they're the same person. Models get confused, quality drops, and the larger the scale, the worse it becomes. Monolith said no more. Instead of forcing IDs into collisions, it created a custom embedding table using a structure called cuckoo hashing. Picture two tables, each with its own unique hashing function. When you insert an ID, you try placing it in the first table. If that spot is full, you evict the old occupant and move it to the second table. If that's full too, you evict again. This dance continues until everyone has their own spot, or the system decides to reshuffle. The result? A massive, dynamic, collisionless key-value storage for embeddings. Every ID gets its own home, no forced sharing. But there's still a problem. You can't keep everyone forever. In the real world, IDs follow a brutal law, the long tail. A few users and items dominate interactions, appearing millions of times. But the vast majority show up maybe twice. These rare IDs don't contribute much to model quality. They're simply too little data to learn meaningful embeddings, and keeping them around wastes precious memory. Monolith gets ruthless. It filters IDs before insertion based on frequency thresholds. Low-frequency IDs are rejected. It also uses probabilistic filtering, a smart way to drop IDs that aren't expected to matter. And for those that do make it in, they come with an expiration timer. If an ID stops appearing, it eventually disappears from the table, like a star fading from the sky. This ensures only relevant, active IDs consume memory. Next comes the real magic: online training. Imagine the loop inside a typical recommender system. A user opens the app. The model ranks items. The user reacts, clicks, watches, skips. Those reactions provide the truth the model was trying to predict. But in traditional pipelines, this truth must wait. It gets logged. It gets stored. It waits for batch training. Hours or days later, the model finally learns what happened. Monolith cuts that loop from hours to minutes. The system uses a sophisticated streaming engine built on Kafka and Flink. When a user takes an action, a click, a like, a scroll, that event is sent to a log queue. Meanwhile, features for the item and user are flowing into a separate queue. Flink joins these streams in real time, matching actions with features using unique request keys. But real-world logs arrive out of order. Actions might show up before features, or hours later, if a user buys something days after seeing it. Monolith handles this using both in-memory caches and an on-disk key value store that holds rare, delayed pairs. Once the features and actions are joined, they're packaged into training examples. These examples get sent to both batch training pipelines and, more importantly, directly to online training. Online training workers consume this non-stop stream of fresh examples, updating the model's parameters continuously. No epic cycles. No waiting for retraining. Just a living, breathing model that adapts instantly to user behavior. But how do these updates reach the serving system? That's where parameter synchronization becomes crucial. The recommendation model isn't small. It's not even huge. It's terabytes. You can't simply replace the entire model every time new gradients are applied. Serving must stay online, uninterrupted. Monolith's insight is simple yet powerful. While dense parameters barely change from batch to batch, sparse embeddings update constantly. So instead of synchronizing everything, Monolith only pushes incremental updates, specifically the embeddings of IDs that were touched since the last sync. In a typical minute, maybe 100,000 IDs get updated. That sounds like a lot, but it's tiny compared to the billions total. The system syncs those updated embeddings to the serving machines continuously, with an astonishingly lightweight footprint. The serving system absorbs these updates without pausing. No downtime. No double memory usage. Just smooth evolution. Meanwhile, dense parameters sync far less often, maybe once a day, because they evolve slowly thanks to massive datasets and momentum-based optimizers. With this setup, Monolith achieves something extraordinary: a recommendation model that is almost always fresh. Fresh enough to track concept drift minute by minute. But real-world production systems fail. Machines crash. Parameter servers die. Networks hiccup. Monolith needed resilience, but full snapshots of terabyte-scale models are expensive. The team tested something bold. What if they only snapshot once per day? Surprisingly, the model barely suffered. Because even in the worst-case scenario, losing 1 day of updates, the actual impact per server is minuscule. Imagine the model is sharded across 1,000 parameter servers. If one fails, you lose the updates for just that shard. And since the loss affects only tiny fractions of users and items, the effect on global accuracy is negligible. This is one of Monolith's core philosophical breakthroughs. Real-time model freshness is more important than absolute parameter durability. In other words, it's better to be up to date than perfectly backed up. Now, how well does this work in practice? The results are stunning. When comparing collisionless embeddings versus hashed embeddings with collisions, Monolith consistently outperformed the old approach in every test. On datasets like MovieLens, models using collisionless tables achieved higher AUC, trained faster, and remained more stable even as user behaviors shifted over time. In internal production tests spanning massive datasets and hundreds of embedding tables, the story was the same. Removing collisions boosts accuracy significantly. Then came the tests on online training. Using datasets like Critio's multi-day click logs, the researchers simulated different synchronization intervals: 5 hours, 1 hour, 30 minutes. The shorter the interval, the higher the online serving AUC. Even a move from 1 hour to 30 minutes produced measurable gains. Live A/B tests in production told the most dramatic story. Real models serving real ads showed double-digit AUC improvements when shifting from batch-only training to Monolith's real-time approach. For recommendation systems, that's huge, the kind of improvement that directly translates to higher user engagement and better business outcomes. And all of this, the collisionless embeddings, the online streaming architecture, the incremental synchronization, the fault-tolerant strategy, comes together to create a system capable of supporting one of the fastest-growing, most behavior-driven platforms on Earth. At its heart, Monolith isn't just a technical achievement. It's a statement. A statement that recommendation systems must evolve, that models must become alive, adapting, reacting, learning in real time. No more stale snapshots. No more waiting for retrains. No more collisions and massive embeddings. This is the future of personalization. A world where the model changes with you, learns from you, anticipates you, and all of it happens invisibly, in milliseconds, powered by architectures like Monolith. If you enjoyed this deep dive into one of the most advanced real-time AI systems ever deployed, hit that like button, subscribe, and drop a comment telling us which foundational AI paper you want us to break down next. Your support helps us keep exploring the hidden algorithms shaping the world. Thanks for watching, and I'll see you in the next one.